Hello friends, in this video we discuss about the integral transforms. In this very first video on the integral transforms, we see the definition of integral transforms and various examples of integral transforms. The integral transforms the integral transforms, which is we denote by f of x of the function f of x with kernel which is function of s and x is defined as I of f of x. I stand for integral transform. I of f of x equal to capital F of s. This is an integral transforms and its definition is integration from a to b f of x into kernel, which is function of k of es and x with respect to dx. This is the general definition of integral transforms. I of f of x equal to capital F of x, which is equal to integration of f of x into k of s comma x. K is kernel which is function of two variables es and x, and it is a definite integral between the limit a and b. So a known example of this integral transform to you is Laplace transforms, where this kernel k of s comma x is equal to e raised to minus sx, and we know that this Laplace transform of f of x equal to capital F of s, and this is equal to integration 0 to infinity e raised to minus sx into f of x into dx. So this k of kernel is just, we have taken a function as e raised to minus sx, simple function e raised to minus s into x. Then limits are from 0 to infinity, then it is called as a Laplace transforms. Second example of this is Fourier complex transforms. Fourier complex transforms. Here the kernel k of s comma x equal to is e raised to minus I s x. Then we denote this Fourier complex f of capital F of small f of x equal to capital F of s equal to 1 divided by under root of 2 pi integration from minus infinity to infinity f of x into e raised to minus sx into dx. So this is the Fourier complex transforms, and we have an inversion formula for this Fourier transform. Inversion formula, and this is equal to f of x equal to 1 divided by under root of 2 pi between the limit minus infinity to plus infinity capital F of s e raised to minus isx into ds. This is the inversion formula for Fourier complex transform. So these two examples, from these two examples you can see that how we get various different forms of the integral transforms. Okay, so third one of this form is Fourier sine transform. Number 3, Fourier sine transform. Fourier sine transform, where k of s comma x equal to, in this is sine of sx, and here Fourier sine transform of f of x equal to, we attach s to differentiate this with other transforms. This is equal to under root of 2 divided by pi, and it is from 0 to infinity f of x into sine sx into dx. Again we have an inversion formula for this Fourier sine transform. Inversion formula f of x equal to under root 2 divided by pi, and its integration 0 to infinity capital Fs of s sine sx into ds. This is Fourier sine transform. Similarly, Fourier cosine transform. Fourier cosine transform, and in this Fourier cosine transforms, here kernel value is cos of sx, and this is equal to f of x equal to this c as a suffix to differentiate this as a Fourier cosine, under 2 divided by pi, integration 0 to infinity f of x into cos of sx into dx. From this you can write the Fourier inversion formula for this inversion formula. So what will be the inversion formula? You can guess. It is simple, root 2 divided by pi, integration 0 to infinity. Here just here replace this term Fourier cosine f of s into cos of sx, and this is with respect to s. So this is about Fourier sine and Fourier cosine transforms. Now we have another example of this integral transforms. Number 4, Hankel transform, and in this transform, to obtain this transform, we replace kernel with the function x into capital Jn of sx, and we denote this by h of f of x. H of f of x equal to f of s, and its limits are 0 to infinity f of x into Jn of sx into dx. This is the Fourier, this is the Hankel transforms, and inversion formula f of x equal to integration 0 to infinity s into f of s into Jn of sx into ds. You can see here x instead of x, we have s here in this inversion formula. Next one is Hilbert transform. which is obtained by replacing kernel s comma x equal to 1 divided by s minus x, and here the capital F of x Hilbert transform equal to 1 divided by pi between the limit minus infinity to plus infinity f of x divided by s minus x into dx, and its inversion formula f of x equal to minus 1 divided by pi integration minus infinity to plus infinity capital F of s divided by s minus x into ds. This is inversion formula for Hilbert transform. And we have another example of this integral transforms, that is Mellin transform, number 6 I think. Mellin transforms, which is obtained by replacing the kernel s comma x with x raised to s minus 1, and we get Mellin transform f of x equal to capital F of s, and its limits are 0 to infinity small f of x into x raised to s minus 1 into dx. So this is the Mellin transform. So these are the all various different transforms which we can obtain from the integral transforms. This will be very helpful to remember while when for multiple choice type of questions. It may be ask these different forms, and you can easily remember these different forms of these integral transforms. Thank you friend, thank you for watching the video.